Okay, so this is chapter 6, chemical energetic. Okay, so energetic of reactions. Then we talk about the energy, the heat energy of a chemical reaction. Okay, so the first point, exothermic reactions. One that releases heat energy into the surroundings. Okay, so I draw pictures to let you imagine. So it's something like this. If you have a container, the chemicals is in the solution, let's say. So exothermic is where the heat release to the surrounding. The heat release from the chemicals to the surrounding. So that means to the water, to the solution. Okay, so the solution here is the surrounding. So we should expect the solutions to increase in temperature. The solutions is expected to become hot in exothermic reactions. So second point, endothermic reactions, one which absorb heat energy from the surrounding. So it is the other way around. So let's say I use green color. The solutions will supply heat to the chemicals. Okay, so that means the chemicals absorb heat from the surroundings. The one which absorb heat energy from the surrounding. So we should expect in endothermic reactions, the solutions become cold. Okay, so next point, bond breaking is endothermic. Bond breaking is endothermic. So this should be reasonable. You know, you want to break the bond, you need to absorb energy, then they use the energy to break the bonds. Okay, so that's why bond breaking is endothermic. They need to absorb heat energy from the solution, they use the energy to break the bonds. Okay, so bond making is exothermic. This is just the other way around. So when chemical bonds is formed, heat energy is released to the surrounding, and that is exothermic. Now we put in 2 columns so that we can see the difference. We can compare between exothermic and endothermic. First point, energy given out to the surroundings, energy is taken in from the surrounding. Okay, so surroundings become hot for exothermic, but endothermic surroundings become cold. Third point, bond making for exothermic, bond breaking for endothermics. Okay. Then we can see the difference in terms of the energy level diagrams. So energy level diagram is energy versus cost of reactions. So cost of reaction is something like the progress of reaction. The progress of reaction. So it's something like this, like time, something like time. Okay. The reactions, you put them together, then they get activation energy. Okay, so and when it has activation energy, then it start to react, and then form products. Okay, form products. Exothermic is where the energy is given out to the surrounding. So because of that, the reactant is expected to have less energy. Less energy because energy is given out to the surroundings, right? So when the reactants form products, the product has less energy as energy is given out to the surroundings. So it goes down. It goes down. Okay. Now, the other one, for endothermic, the reactants need to absorb energy from the surroundings. So we have activation energy also. Activation energy. After that, absorb energy from the surrounding. So the product has more energy than the reactants. Okay. So the thing is, uh, exothermic release energy, energy decrease. Endothermic energy increase. But what about activation energy? So activation energy is actually what? So activation energy is the energy required to make reaction able to happen. And so we need to have activation energy. It's something like, you want to score chemistry. So you must have activation energy. You must have activation energy to make yourself more aggressive, study harder. So activation energy. So once you have activation energy, you are activated, and then you can have good results. Okay, you can go to higher level. Go to higher level from IGCSE, then go to college and university, something like that. Okay. Now, bond energy. Bond energy. This is the amount of energy consumed or liberated when a bond is broken or formed in kilojoule per mole. So we discussed just now, which is here, bond making, exothermic, bond breaking, endothermic. So that means when it comes to this point, we have to understand that energy is consumed when bond breaking happens. Bond breaking, bond breaking, bond breaking, energy is consumed. That is endothermic. Okay, the next one is bond formation. Bond formation is energy, as you can see here, bond making, exothermic, right? So energy is liberated. So that is energy is released to the surrounding. So exothermic. Okay. Now let's see the equation here. Delta H equal to bond breaking plus bond forming. So to get the delta H is basically here to here. Here to here is delta H. The difference between reactants and products. So another example you can see here, product, reactants. So the difference between product and reactants is the delta H. So you want to find the delta H, you take bond breaking plus bond forming. But you need to know that bond breaking is a positive value because endothermic is positive. Bond forming is automatically a negative value because exothermic is negative. Exothermic, negative. How to remember it's negative? It's go down. From here, go down. So negative. This one is positive because it goes up. It goes up. Going up is positive. So why bond breaking plus bond forming? So imagine that. Let's say I give you one simple example. So let's say Haber process. Nitrogen plus hydrogen. I draw the chemical bond also, become ammonia. Okay, so I balance it. So I put 2, then I put 3 here. So bond breaking. Bond breaking is happening on the reactants. So the N triple bond N, you need to break the bonds to N and N. Okay, the hydrogens, you need to break the bonds to H and H. Try to imagine that, to H and H. Okay, you break the bonds of the reactant first. That is bond breaking. The bond breaking, the energy involved is a positive value because it's endothermic. Bond breaking is endothermic. So you have positive values here. Now you have atoms now. After bond breaking, you have atoms. You have nitrogens, 2 nitrogen atoms. You have 2 times 3, 6 hydrogen atoms. So times 3, yeah. Okay. So imagine now you have 2 nitrogen atoms and 6 hydrogen atoms. Now you need to form chemical bonds so that ammonia is formed. So what happened here is 1 of the N and 3 of the hydrogens need to form chemical bonds to be ammonia. Okay, so to be ammonia. So of course, times 2 to form 2 ammonia. So bond formation. So bond formation happens at the product site. So this is bond breaking, and that is bond forming. Bond forming is negative. This is positive. So let's say you count the bond breaking, you get positive X kilojoule per mole. You count the bond forming, let's say, it's negative, right? Bond forming is negative. Huh? You get negative Y kilojoule per mole. Huh? Okay. Now you want to find delta H? You just take bond breaking plus bond forming. Then you count. If this is positive answer, then Haber process reaction is endothermic. If you count this, you get negative. That means this reaction, Haber process, is exothermic. So that is what are they trying to say. Okay, now let's move on. If overall heat energy is negative, that means you count this, you get negative. That means the reaction is exothermic. If overall heat energy is positive, so in other words, that means you go and count this, you get a positive answer. That means reaction is endothermic. So it means something like that. Okay, now let's look at the next point. Productions of energy. A fuel is a substance which can be conveniently used as a source of energy. So for example, fuel, petrol, source of energy for the car. Burning fuels like oil to form oxides is an exothermic reaction. Okay, so you burn fuels, you burn the petrol to form oxides, carbon dioxide. So that is exothermic reaction. It releases heat to the car engine to move the car. The heat from burning fuel is used in power plants to create steam from water and turn turbines. Okay, so one of the famous example is the burning of coal. Burning of coal. So you burn the coal. The coal is used to heat up the water. So the water turns into steam as it boils. And then the steam has moving around quickly because it has kinetic energy, high kinetic energy, and it turns the turbine. So once the turbine starts to spin, Then we have the electricity generated. Okay, so of course that is physics. How it generates, we don't want to care first. That's under physics. Okay, so it produces energy. What we can conclude here is burning of fuel at the end produce energy, produce electrical energy. So in order for any material to combust, three things must be present: fuel, heat, oxygen. So you need fuel to burn. You want to burn, you need heat. So the fuel will react with oxygens to form carbon dioxide, for example. Okay, so now a good fuel would be cheap. Okay, so for example, coal or petroleums that are kind of cheap. That's why it is popular nowadays, because it's cheap basically. If it's not cheap, they may think of alternative. Maybe they want to use palm oil. Palm oil, why it's not popular? Because it's expensive. Okay, so cheap is one of the reasons why petrol, diesels are popular. Even coal. Okay, coal is also popular because it's cheap. Okay, be available in large quantities. Okay, it's available. Okay, so we have many countries that produce petroleum and exports to other countries, so it's available. Okay, be a liquid at room temperature. For example, petrol, diesel, they are liquid. They are liquid. Of course, coal, maybe coal is solid, so it's okay. So we can just transfer it to the power plant and burn it. Okay, so we are not talking about the putting coal in the car and burn it in the car, so we don't want to do that. Okay, so for car, liquid is good. Okay, liquid is good. Petrol or diesel to fill in the fuel tank. Produce a large amount of energy when combusted. So that happens to petrol and diesel. Not produce polluting gases. So petrol and diesel, yes, they produce polluting gases. So although it producing polluting gases, but we are still using it because it's cheap. So money is the main concern of human being also. So although it is polluting, we are still using it. Okay, so that's the problem. Okay, because it's cheap we have fuel that doesn't produce polluting gases, like electric car, for example. It doesn't produce polluting gases, but it's expensive. So the main concern is money. Okay, now that's the thing. Okay, let's continue. Next point. As you can see, this chapter is kind of short. After this, no more already. Okay, then we can do questions. Okay, now let's continue. Hydrogen. Burn explosively with oxygens. So if you remember the observation that we normally say, hydrogens burn with pop sound. Hydrogen burn with pop sound. So that is burn explosively. That's why you can hear pop. Okay, so that is a small explosion when oxygen and hydrogen react.
So oxygen burns glowing wooden splinter, lights up glowing wooden.
Light up. You can see here. It is used in rockets. So it is used in rockets. Which means what? Rockets use hydrogen as fuel. In a fuel cells use hydrogen also. What is fuel cell? Fuel cell is used in electric car. In the fuel cell, it combines with oxygen without burning. Combine with oxygen without burning. So rocket, yes, we burn the hydrogens with oxygen. But in fuel cell, in electric car, don't expect any burning happening. So no, hydrogen react with oxygen straight away without burning. Produced by reacting with methane gas with steam. So that is how we produce hydrogen gas, methane gas with steam. Okay, let's see whether we can make the equation straight away or not. So imagine that methane gas is CH4, steam is H2O. So it produces hydrogen gas. We use it as fuel. Okay, so what else? H2 has been used, so we should expect CO2 to form. CO2, so H2, okay, let's balance the hydrogen. So currently we have 6 hydrogen. Okay, let's balance the oxygen first. We put 2 here, 2 oxygen, balance. Now we have 4 plus 4 hydrogen, so which is A. So 4 times 2 is A. And carbon, yes, balance. So that's the equation. Methane gas, CH4, steam, H2O, react, form hydrogen gas. Hydrogen gas is used in rocket, hydrogen gas is used in fuel cell. Okay, so the advantages of using hydrogen as fuel. Produce a lot of energy. It's enough to make the rocket fly to the outer space. That is enough. That is a lot. Abundant on Earth. Sea. Okay, so that means the sea has a lot of hydrogens. How? Okay, so of course they don't give any detail. Sea, sea water, H2O, H2O. Okay, less pollutant, less pollutant. Of course, you burn hydrogens, less pollutants produced because hydrogen react with oxygen to form H2O, so not so polluting. Renewable fuel, renewable fuel. Okay, so you can keep producing hydrogen. Disadvantages, difficult to transport as it is a gas at room temperature. Okay, so it's a gas. Hydrogen, use it as fuel. So the problem is you need to carry a hydrogen gas tank. That's the thing. Okay, so imagine a car with a gas tank inside. So it occupies space. So you can't put much thing in your bonnet already because of the gas tank. Form explosive mixtures with air, very dangerous. So when it exposed to oxygen, then explosions. Okay, now let's see the next part. Simple cells. A cell is a device which converts chemical energy into electrical energy and is composed of two metals of different reactivities connected by an external circuit and an electrolyte. So if you remember just now in the chapter 5, right? So I said we have electrolytic cell and voltaic cell. So electrolytic cell is chapter 5. Then I said voltaic cell is not in the syllabus, right? So actually it is here. It is in chapter 6. It's in chapter 6. Now this simple cell is the voltaic cell that I said. The voltaic cell. Voltaic cell. The voltaic cell is what? Voltaic cell is just a cell, just something like battery, voltaic cell. It's the one that produce electricity. Okay, so voltaic cell. So now you have to remember voltaic cell like what we discussed just now, voltaic cell, the anode is negative. The cathode is positive. So remember that, okay? Just now we discussed this through also. Now we have to take it already. Okay, now let's see. The anode and cathode, right, must be two metals of different reactivities. So for example, copper and zinc. Copper and zinc. Copper and zinc, it has two different reactivities. Where zinc is more reactive, copper is less reactive. How we know which metal is reactive and which one is not reactive? We have reactivity series to understand it. Okay, we have reactivity series. So we don't want to look at reactivity series first. Let's move on first. Okay, so or maybe I just let you take a quick look on electric reactivity series. Just a quick look from the internet will be good enough. Okay, so let's see. Reactivity series image. Okay, so this is an example reactivity series. So you can see zinc, copper at the bottom, less reactive, zinc on top, more reactive. So this is the series. So basically, you can see the most reactive metals are those in group 1. Group 2 is kind of reactive also. Group 3, then followed by all this. Okay, these are the transition elements. Okay, so group 1, group 2, group 3, then some transition element. Okay, so that is reactivity series. If they are more reactive, that means what? Let's say zinc is more reactive than copper. That means how? So you need to know that the more reactive metals tend to form ions. So let's say zinc is more reactive than copper. So you should expect zinc to form ion. They are more readily to form ion because it's reactive. So when they form ion, they forms electrons also. So that's why zinc has electrons coming out from here at the same time because it forms zinc 2 plus, and the electrons will go through the external circuit and go to the copper. The less reactive metals, copper, so what happens is they tend to absorb electrons. Okay, so from here, accepting electrons happens at the positive terminal, which is cathode. So you can see something like this. This is where accept electrons, and this is reduction. So from here, you will understand something. Compared to electrolytic cell, right? This is opposite. But this and this are same. Cathode, reduction happen at cathode. Accepting electron happen at cathode. So no matter voltaic cell or electrolytic cell, these are true to both of them. It's just that they have different charge. Anode, this is what happened at anode. Zinc becomes zinc 2 plus. This is oxidation. This is lose electrons. Oxidation. So again, compared to electrolytic cell, this is different. But these two are same. So you need to know that. So the process works due to the different reactivity of metals. The more reactive metal will donate electrons. The less reactive metal will take electrons. Okay, so takes electrons, something like this. Cu2 plus, take electrons, become Cu. Okay, now consists of a negative pole. Negative pole is the one which is the more active metal. Zinc, more active. So it is negative. It's negative. Huh? Negative is anode. Negative is anode. Oxidation happen in anode. So that's why loose electrons happen there. Loose of electrons. Okay. Now, and a positive pole less reactive metal. For example, copper. And then electrolyte. So electrolyte is here. Ammonium chloride as our example. And the greater the difference in reactivities of the two metals, the greater the voltage will be. So they are trying to say something like this. Let's look at the reactivity series just now. If you use, let's say, for example, I use potassium and gold, very big difference in reactivity. This is very reactive. This is very less reactive. The voltage should be very big. The voltage produced by these two will be very big. So if you just use zinc and iron, zinc and ferrum, ferrum means iron, so they have small difference in reactivity, so the voltage will be small. Okay, so something like that. So of course, voltage cell, right? We should expect a voltmeter to be used. Maybe here, you can put a voltmeter here. If you don't want to put voltmeter here, you can put some electrical device like light bulb, that will just light up the light bulb. Or you just put voltmeter here. You put voltmeter here, we call it voltage cell. Voltage cell means voltmeter is there. So it's related in that way. Now let's continue. This point, the electron flow because one metal is more reactive. That means zinc, more reactive, produce electrons. So it has a stronger drive to give up its electrons. So give up its electron here. And the electron flow through the external circuit. The atoms give out electrons and enter the solution as ions. So the zinc, which becomes zinc 2 plus, zinc 2 plus enter the solution. And finish. So that is the end of the simple cell or voltaic cell. Okay. Now, at the end, radioactive isotopes. Uranium-235 can be used in nuclear power station to produce electricity. Nuclear power station. So that means this is uranium-235. We use it to produce nuclear energy. Okay. So uranium-235, in Russia, there is a lot. So uranium. So uranium, you can get a lot from Russia. And then they take the uranium-235, and what happened is uranium-235, you see 235 means the nucleon number is big. So it's a big nucleus. So you can break down the big nucleus to two smaller nucleus, and that is called nuclear fission. Nuclear fission, break down the big nucleus to two smaller nucleus. That is nuclear fission. So nuclear fission release a lot of energy. That is exothermic, right? No? The radioactive isotope is bombarded by neutrons. So you take a neutron to collide with the uranium-235, and then it breaks down, resulting in a lot of heat being produced. So it's a big uranium-235 nucleus. You use neutron to collide with it, and then it breaks down. The nucleus breakdown. Nucleus breakdown, then a lot of energy is released to the surroundings. Small amount of radioactive fuel produce large amount of heat. Okay, so maybe you just use 0.1 gram of uranium-235, then you can get a lot of energy. So advantages, lots of energy is from a small amount and no carbon dioxide. Okay, so compared to the burning of fuel, which produce carbon dioxide, this one, no. Disadvantage, radioactive waste produce. So when you break down the uranium-235 to form two products, the products are radioactive. Okay, so which is dangerous. Okay, which has radioactive ray. So dangerous. So you need to bury it underground for years. So if you accidentally take it out and play it around, then you get radioactive exposure and get skin cancer. Okay, and non-renewable. So once uranium-235 has been used up, then no more already. No more already. So non-renewable. Okay, so finish the theory part.